Thank you everyone for being here. We're very excited to give this talk. So I'm Claudia. So we're going to talk about challenges and opportunities that we faced while running and also setting up and deploying large-scale GPUs clusters for our AI workloads. So we're going to start with a brief introduction of what type of clusters we're talking about, so both on the hardware level and software level. And then we're going to focus on how do we run the AI workloads and how do we monitor them. And that would be the observability, fault detection, and recovery, and fault recovery part of the presentation. And then we will wrap up with some takeaways. All right, so GPU clusters, that's what we're talking about. So we've been running AI workloads on 2 generations of distributed clusters with GPUs. We have our first generation is Cloud Vela, is deployed and running on IBM Cloud, and is composed of several compute nodes, each of them having 800 GPUs, NVIDIA GPUs, all of them connected through, of course, NVLink and NVSwitch. In addition, we have a total of 800 gigabit per second network in and out between the nodes. And of course, there is always some storage connected, so we have about 3.2, I think, terabyte NVMe drivers. So that's the one that you can see on the left-hand side. That's Vela. On the right-hand side, we have a bumped up version of Vela, is Vela 2. This one runs, each compute node has 8 H100 NVIDIA GPUs, all connected through NVLink, of course. And we have a big bump up on the network in and out from the node. We ramped that up to 3.2 terabit per second. We have storage, it's about twice the size of the previous Vela generation. And yeah, so this is, those are the clusters where we are running our training and inference workloads. So that's the hardware. Let's talk about the software. So we run Red Hat OpenShift as a base platform, running to also be able to exploit the network. We run the multi-NIC CNI to access all the ports that are available for each pod. As you can see, everything is about AI, and with this cluster and the software stack we deploy, we're able to cover pretty much the entire life cycle of any AI workload, going from data pre-processing, training, fine-tuning, and model serving. Each job can be small or large. Few GPUs, 1 GPU, or hundreds of GPUs. Of course, that depends on the type of workload. So you can imagine AI training is going to take the largest chunk of GPUs available. And since this is a multi-tenant cluster, of course, you need to have support for priorities, preemption. Of course, the idea is to try and have the best usage possible of the cluster. So in this presentation, we're going to focus on workload management. Workload management and in cooperation with observability in the cluster. So you may have seen that Kueue and app wrapper in the previous talk. So that's where we are, and that's what we're going to talk about. So still in the software stack, ML Batch is the workload and resource management for batch AI and machine learning workloads on Kubernetes. This is all open source, of course. It's integrated with all the AI framework and runtimes that we've seen also throughout the morning presentation and the Kubeflow panel. So that's all there. And what is the major focus, as I was mentioning, is to be able to run efficiently a multi-tenant cluster. So we want to make sure that users and admin can all access the cluster and use it in a fair way. So we provide teams, queues, priority, and enforce quotas. And we want to make sure that productivity and cluster utilization is at the best possible. GPUs are expensive. We have been saying that also this morning. And we don't want to have them just sitting idle while they could be utilized. And of course, fault tolerance, especially for what concerns the workloads. We want to make sure that the user can just forget that their workload is running. In case something happens, the workload should be able to recover by itself. And the fault tolerance and productive utilization part, that's what is also working in collaboration with all the monitoring parts. You can see this. The monitoring phase is going throughout the entire life cycle. All right, so that's about software and hardware. Let's dive into the main topics. So why do we need advanced fault tolerance? It's a naive question maybe, but we also have to take care of that. So in an ideal situation, and in ideal world, you would not have any human intervention whatsoever in your cluster. So you just, the usual cloud thing when you say click button and run everything, and I then come back and everything is done. And that everything is done means also that if something happened during the cluster or in the cluster, or the workload stops, or any type of fault, crash, or anything, that would be managed by the cluster automatically. So this means, of course, also cleaning up resources where jobs are done so that those resources can be used by other teams and other workloads. Also, given the current utilization of the cluster, you can also do some adjustment to quota and match also the actual cluster capacity. And I want to focus on the actual cluster capacity because it doesn't mean that the capacity or the number of GPUs are always the same, because some crash can happen, also hardware faults, and the GPUs, some of the GPUs might not be available. So you want a system that is able to avoid the GPUs with severe faults. So not having workloads running on those jobs, because where they're gonna fail. And there is evidence of that. This in particular is a set of screenshots that I took from three main places. One, on this side, this is one of the major latest white paper that have been released by Meta. This is for the training of the Llama 3 herd of models, where they reported nice table saying what went wrong. And there's a lot of things that went wrong. And especially on the hardware level, they report 78% of the actual faults, so when the workload would stop, was because of hardware failures. And almost 60% of those were GPU's failure. So that can be a major blocker for the workloads that are running on the cluster. Another very recent technical blog from NVIDIA showing failures and reasons why their training job failed over a range of 4 months, I think. Those are both hardware and software failure. And also at the very bottom, there is a very recent paper published by University of Illinois Urbana-Champaign and IBM, where there is a very intensive analysis of the workload failures, especially when concerning GPUs in that table. And they reported over a time frame of 2.5, 3 years, there were more than 4,000 job crashes because of hardware failure. So this is something that you really want to take a look at. Monitoring, that's how you do. And there are, of course, native tooling that we're all familiar with. Prometheus is the major go-to on Kubernetes platforms. That's what we use, what everyone uses. And it provides information about workloads, Kubernetes infrastructure, node, network, and all of that. On the GPU side, we have the DCGM exporter that you can install along with the GPU operator. And that provides a lot of metrics from the GPUs. And that will tell you GPU utilization, power, errors. There is a good chunk of information that you can get. Grafana is great for visualization. So that's, of course, something that you want to have handy instead of going and query all the metrics all the time. You just want to see what's happening. We've built a custom solution for our clusters based on the experience that we've been gaining while running those workloads and running the clusters. That's called Autopilot. And this runs health checks on the cluster, which are things that you would not immediately see from the existing metrics. And we're going to dive into that. So the Autopilot tool comes from our experience and what we have learned by running Cloudvela. So we know that there are some common infrastructure errors that are affecting the AI workloads, and those were some that we were not be able to find through the existing metrics. So we had to package those things, and we want to run those as periodic health checks because we know those errors can occur all the time. So you want to have something that will tell you when those are happening. And this doesn't really, it's not just about GPUs, it's also about network and storage. And once you're running, you know which tests you want to run, you know how to run them. Of course, you want to see what the results of those health checks, and you want to see them through Prometheus metrics. That's the best way to show metrics on Kubernetes systems. We also decided to add an extra action, which is to label the nodes with the result of those tests, so that also the administrators could take action if they wanted on the cluster. And also, those are the easiest way to have other tools steer the workload's lifecycle. So just to wrap up, we built this tool, Autopilot, which runs health checks. These health checks, GPU, network, and storage, they are periodic. They run all the time on the cluster and continuously check what is going on. The metrics are exported through Prometheus, and then we label the nodes so that other tools like scheduler, queuing system can take action based on the current health of the node. That's a list of the health checks that we run. So all of those are information that you can really get from like GPU remap rows or the power throttle. You get those by running an NVIDIA semi command. So we're not really inventing anything here. We're just reusing what we have. It's just that that information that's listed here is not available through the DCGM exporter, for instance. So you need to check those things manually and report when an error is happening. Some problems may be more or less problematic to the workload. So some can just imply that there is a degradation in the training performance, for instance, while some other you just want to remove the job from that node, reboot the node, take care of the node because the job is going to crash. And also you want to run extensive diagnostic on the GPUs that we can do through the DCGM tool provided by NVIDIA. So those are all things that help us to steer the workloads and keep the utilization of the cluster very, very high. And with this, I'll pass it to David.
Okay. All right, so thanks. So now that we've, Claudia's talked a little bit about how we do the automated fault detection in our clusters, I'm going to talk about fault recovery. So to get there, first I need to talk a little bit about some of the components in our system. So we've heard about Kueue in the previous talk. It's a Kubernetes native system to manage queuing, quotas, and jobs. So Kueue on our clusters, Kueue is responsible for deciding when jobs should wait, when they should be admitted, which means their resources and pods get created, and when a job should be preempted, so the pod's deleted. And the key abstraction that Kueue uses to do this, one of them is something called a cluster queue. So cluster queues are assigned quotas. Users end up submitting their jobs to cluster queues. The cluster queue logic is what decides which jobs should be admitted, when they should run. And the cluster queues are grouped together into cohorts. And in particular, within a cohort, so you can have multiple cluster queues in a cohort, those cluster queues are assigned quotas, and they can borrow quotas from each other. And that borrowing mechanism is one of the key mechanisms we use to deal with varying size clusters. In particular, what we do in our clusters in ML Batch is we reserve a few nodes of resources as what we call a slack cluster queue. So this picture on the bottom is showing a typical setup in one of our clusters where we have a whole bunch of nodes. Those are the little boxes on top in green or red. The green nodes represent healthy nodes whose resources are available. And there are a few nodes whose resources are unavailable. Those are red. And then the entire capacity of this cluster is sliced into pieces and assigned to various teams. And we do that basically so that the total quota, including the Slack capacity assigned to the Slack cluster queue, adds up to the total available resources on the cluster, healthy and unhealthy. And then our system automatically watches nodes. It sees the labels put in by Autopilot, and it automatically adjusts what Kueue calls the lending limit, the amount of capacity that the Slack cluster queue is making available to other queues to borrow to match the actual available capacity. So this is how we're able to sort of smooth out these sort of small amounts of failures, nodes coming in and out of clusters. All right, so this gives us several benefits. It helps us prevent from admitting too many jobs. It gives us ability to reserve quota to sort of migrate those jobs away from unhealthy nodes and have space for them on healthy nodes. And also, it also lets us sort of view system maintenance as just another reason for things being unhealthy. So it's very easy for administrators with this kind of setup to go in and cordon some nodes. A cordon node looks just like an unhealthy node as if it was from Autopilot, and we can go ahead and deal with that capacity thing. So we have maintenance happening without really disturbing things at all. All right, the second thing is App Wrapper we've heard about. So App Wrapper plays several roles in our software stack. It has two of the key things I want to talk about. First, it lets us group multiple resources together as a single workload. So some of our workloads are more complex. They may have multiple kinds of compute resources. They may have auxiliary resources such as services, secrets, or ingresses. And so we put all those inside, our users put all the resources for their job inside a single app wrapper, and that's what gets admitted or queued or preempted by Kueue. And so let's just keep all this stuff together and manage it as a single thing. And for this talk, the key things that App Wrappers does is App Wrapper is also our mechanism for hardening the workloads. So the App Wrapper controller monitors the workload health, ensures that if something goes wrong with the workload, that the resources are robustly cleaned up so that they're actually all gone and we don't have dead pods lying around sort of tying up resources. And it gives us a uniform way to talk about our retry and failure policy, which I'm going to talk about next. And we have an integration with Autopilot with it. In particular, there are a lot of reasons why a workload might be unhealthy. Pods could fail. There might not be enough running pods for a variety of reasons. An image pull problem, some kind of scheduling problem, fragmentation preventing from running, and so on. And so the basic way the App Wrapper does this is it sort of monitoring the pods and their health. It gives the underlying controller, for example, the PyTorch, the trainer operator, the job controller, it gives it a chance to try to clean up. But then if it looks like the base controller for the resource has not managed to recover the workload, then the App Wrapper controller will kick in and go through our fault tolerance, our life cycle. The picture on the side there shows the App Wrapper life cycle. And so basically, at the high level, an App Wrapper is suspended or it's admitted. When it's admitted, queues decided it could run. It has quota assigned to it. It has resources being created, and it's running. Within that admitted state, there basically are three substates. So resuming means the app wrapper has been started to run and it's creating the other resources, the PyTorch job, the pods that belong to it, the job object, and so on, and those are being scheduled. Running is a sort of normal state for it, and then from running it can go to succeeded or failed. If the app wrapper controller decides that something is wrong with it, then we hit this reset phase, and that's when all the resources are removed and then potentially re-executed again, and we go around that loop some number of times. And there's sort of this uniform retry loop will retain the quota, so we have still the ability to run, do the reset, and then go ahead and do that. And we configure the system so there's a reasonable sort of defaults for all these various pause times and grace periods and retries. Those can be set by the cluster admin and can be enforced, and then users can override them within limits on individual jobs using annotations. And so putting it all together, we have Autopilot and the tools it uses, checking the GPUs, checking the network health, and labeling nodes to tell us what's going on. The app wrapper controller automatically injects affinities into all the pods that are created for the workload. So this helps us steer away new workloads from unhealthy nodes. It also, it's part of its monitoring, is it detects pods that are running on nodes that have now been labeled as evict by Autopilot. When that happens, it'll go and trigger a reset that will result in the pods being removed and sort of automates this whole recovery from the failure. And with the integration with the Slack cluster queue with Kueue, we do capacity management. So we adjust the available quota that Kueue is using to admit jobs based on what's healthy in the cluster. All right, so what I'm going to do now is show a demo of all this working together. It's always fun doing demos. All right, so this is a recorded demo, and so here we do is we're going to submit a workload. This is a relatively small demo cluster we have. We have 3 nodes in it, and so we're going to have Alice submit a batch workload that's going to use 2 of those nodes. All right, and we can see them running in there. We're seeing where the pods are, and now what we're going to do is we're going to pretend to be Autopilot, and we're going to label a node as if there was a failure. All right, so we're going to go in, grab one of those node names, and we'll label that node with the label that Autopilot uses to indicate there's a severe failure on that node. So any workload running on that ought to be migrated away from it. Okay, so we'll go ahead and watch the thing running. It'll take about 45 seconds for the mechanism to kick in, for the app wrapper controller to see that node's been labeled, to wait for a little bit, and then to go through the reset trial to do that. So while it's doing this, right, so it's sort of monitoring. It notices the node has been labeled, and it will then go ahead and trigger a reset. And as I said before, it has these affinities, so when the new pods get created, they'll have those affinities in them. So after this workload gets cleaned up and recreated, it'll be steered away. The pods will be steered away by the scheduler from the nodes that are unhealthy. And it always, there it goes. So now we finally noticed. So we're resetting. The app wrapper is being resetted. That'll take a few minutes. Now all the resources are completely gone. So it's now safe to go ahead and resubmit it. And if we look at them, we can see that it's running, and none of the pods are running on the victim node that we had labeled. Right? So going back out of there. So just to quickly sum up, so we've talked a little bit today is there are many potential sources of failure, degradation on large ML clusters with GPUs, high performance networks and storage. If you really want to make effective and productive use of these things, you need to have automation so that if something goes wrong, you don't need a human in the loop at 2 o'clock in the morning to come in and fix it. The system can fix it, and you can continue to get high utilization out of it. And we talked today about pieces of our stack, Autopilot and App Wrapper, that sort of capture our experience of these clusters. They're both open source, and they're both parts of our ML batch software stack that we run in our clusters. And if you're sort of interested in this, Claudia, Olivia, and I have a tutorial tomorrow where we're talking about our entire stack. So that's the QR code for that. So we'd love to see some of you there if you're interested in learning more about the entire stack and how we use it. And the other QR code is for you to give us some feedback on the talk. So we'd be happy to take questions now.